In this episode, we'll explore how multimodal LLMs are built and trained. So far in the LLM Chronicles series, we covered the basics of building modern LLMs using the transformer architecture, focusing on text generation. But over the past year, we've seen an explosion of so-called multimodal large language models, such as GPT-4 Vision and Google's Gemini. These models can handle more than text, such as images and even videos. In this episode, we'll look at the details of how these advanced models are constructed. We'll begin by examining the overall architecture of a multimodal LLM and its components. Next, we'll discuss the general training process of a multimodal LLM. After that, we'll focus on vision and explore vision transformers and how they're trained with contrastive learning. Vision transformers are the most commonly used building block for multimodal LLMs with vision capabilities. Finally, we'll get hands-on and look into Google's open-weight PaliGemma model, analyzing its implementation to see all of these concepts in action within a real-world multimodal LLM. As usual, you are on YouTube, so if you want to support this channel, don't forget to like, comment, and subscribe. On top of text, multimodal LLMs are designed to process and understand information from multiple types of data inputs, such as images, audio, and even video. At the core of the architecture is our usual pre-trained LLM, such as GPT-4 or Llama, which is responsible for understanding and generating text. This model acts as the brain of the system, interpreting inputs and producing textual outputs. To extend this capability, we incorporate modality encoders designed to process specific types of data. These encoders take raw inputs, such as images and audio, and convert them into hidden representations that capture the essential features of the input. These representations produced by the modality encoders need to be aligned with the LLM inputs. This alignment is achieved through a modality interface, typically implemented as a multi-layer perceptron. This layer is trained to project the output representations of the modality encoders into the LLM's embedding space. Finally, some multimodal LLMs include modules that can generate outputs in various formats beyond text, such as images, audio, and video. When it comes to modality encoders, instead of training them from scratch, we often use pre-trained encoders. Commonly used image encoders are based on convolutional neural networks or vision transformers, which are trained with contrastive methods, such as OpenAI's SigLIP and Google's SigLIP. Similar approaches are used for audio encoders, such as Microsoft's CLAP, Contrastive Language Audio Pre-training. And given that the essence of video is a sequence of frames over time, video encoders typically build on image encoders, processing frames sequentially and incorporating temporal modeling techniques to handle the sequence of frames over time. Training multimodal LLMs is very similar to training regular text-only LLMs, and it involves three main stages: pre-training, instruction fine-tuning, and alignment to human preferences. Pre-training focuses on learning how to align different modalities. As we already start with a pre-trained LLM and a pre-trained modality encoder, we typically freeze the parameters of these two components. This approach avoids inadvertently losing that pre-trained knowledge. Instead, we focus on training the learnable interface that projects the encoder representations into the LLM's embedding space. This training typically involves predicting captions for images, which is an effective way of aligning the different modalities. Pre-training mostly uses coarse datasets made of web-scraped images where captions are usually brief and noisy, coming from alternative text attributes on websites. More refined datasets do exist that contain longer, more accurate descriptions, providing a finer alignment between images and text. Similar to text-only models, we use instruction tuning to teach the model to understand and follow multimodal user instructions. The datasets used for this training phase include examples with instructions from various tasks, paired with corresponding images and the expected responses. Tasks can be anything, from basic image description to object detection, segmentation, visual question and answering, and so on. The final stage is alignment, where the multimodal LLMs are fine-tuned to match human preferences. This involves techniques like reinforcement learning from human feedback and direct preference optimization that we already discussed in a previous episode. These methods help ensure that the model's outputs align with what users find useful and relevant. Okay, now that we understand how multimodal LLMs work, I want to spend some time digging deeper into modality encoders and how they are created. In theory, we could use a simple multi-layer perceptron like the one that we've trained to recognize digits from the MNIST dataset. However, in practice, we use more complex architectures to address the specific challenges of different data formats. For example, for images, we need the ability to scan the input to recognize patterns regardless of their location in the image. And for this, we can use convolutional neural networks. You're probably familiar with CNNs, as they have been the state-of-the-art in image recognition tasks for over a decade now. However, here we will focus on vision transformers, which have recently emerged as a comparable alternative. Vision transformers leverage the transformer architecture we already know and love, but this time to process images rather than text, and they perform on par with CNNs. Vision transformers were introduced in a paper titled "An image is worth 16 by 16 words." The architecture of vision transformers mirrors that of language transformers, using a series of encoder blocks with multi-head self-attention and feed-forward layers. The main difference is in how they process input. The image is divided into a sequence of fixed-size patches, similar to how sentences are treated as a sequence of words. These patches are then flattened into vectors. For example, a 16 by 16 patch from a grayscale image results in a 256-dimensional vector, while the same patch from a color image with 3 channels for RGB results in a 768-dimensional vector. These vectors are embedded with a linear projection and then combined with positional embeddings. Similarly to what happens with text-only transformers, the positional embeddings allow to retain spatial information. Vision transformers are designed to generate representations that are useful for tasks such as image classification, object detection, and segmentation, much like BERT is used to generate representations for natural language tasks. To achieve this, a special classification token is added to the input sequence of patches, exactly as done with models like BERT. During training, this classification token aggregates information from the entire image and is used to predict the class label. The model is trained on large-scale datasets to minimize classification errors, optimizing the cross-entropy loss. By leveraging self-attention, vision encoders can capture long-range dependencies between patches, and this enables effective image processing, achieving competitive performance when compared to convolutional neural networks. Vision models like vision transformers and convolutional neural networks are traditionally trained to classify images into fixed categories, which limits somewhat their understanding of broader visual concepts. This happens because they optimize their representations to only capture the concepts in the labels, discarding nuances that are not needed for the specific classification task that they're being trained for. However, for many applications, we want models to capture as many of these visual and semantic nuances as possible. To obtain this, we can use contrastive learning methods to better align text with images. These contrastive learning methods are used in models like OpenAI's SigLIP and Google's SigLIP, and they're used to train vision encoders that can capture a wider range of visual concepts. In CLIP, the pre-training task aims to predict which caption matches which image in the training set. A batch of images is fed into the encoder to produce hidden representations for each one. The associated captions are then processed by an LLM to generate text embeddings. The objective of training is to maximize the similarity score, that is the dot product, between the image and the corresponding text embeddings, while minimizing the similarity between the image and all the other text embeddings which are unrelated. In CLIP, this is done using a softmax contrastive loss, which is memory intensive because it requires computing the pairwise matrix of all samples in the batch, while Google's SigLIP uses a sigmoid-based contrastive loss, which operates on individual image-text pairs and does not require a global view of the pairwise similarities, making it more efficient and scalable. The result of this contrastive training is a vision encoder that is semantically aligned with text because it's been trained at scale on pairs of images and associated captions. One remarkable outcome of this approach is the capability for zero-shot image classification. This means that the model can determine which sentence from a set of arbitrary descriptions best matches a given image without additional training. We simply compute the dot product between the image and the text embeddings, and we then select the one with the highest similarity score. While this zero-shot capability is not directly used as part of multimodal LLMs, it does demonstrate the effectiveness of contrastive learning in aligning visual and textual representations, and explains why most multimodal LLMs use vision encoders which were trained this way. Alright, we are ready now to jump into Colab to see all of these in practice. Here I've got PaliGemma, which is a Google open source multimodal LLM. I've already done all the imports, and you are going to need to log in into the Hugging Face hub in order to be able to download the weights of this model. Again, PaliGemma 3 billion parameters, and I've got it already instantiated. Something else that we are going to need for this is the PaliGemma processor, which is going to take the input and prepare it so that Gemma can process it. Now, before using Gemma, I want to show you how this architectural diagram, which applies to all multimodal LLMs, actually relates to the PaliGemma implementation. So we've got the model, and I can just print it. That's a PyTorch implementation. So you can see here the three elements. We have the vision tower, the multimodal projector, and the actual language model. Exactly what we have here. This is the vision tower, so the modality encoder for vision. Then we've got the projector, which is what we call the modality interface, and then we've got the multimodal LLM. Now, if we dive a little bit deeper into these, the vision encoder is just Google's SigLIP vision model, which is a vision transformer. So as you can expect, we've got an embedding layer which takes the input image, divides it into patches, flattens the patches, and then projects them with a linear projection. And then we've got some encoder blocks, exactly as any other transformer. I think we've got 27 encoder blocks here. And then we've got the final projections. The multimodal projector obviously takes the output of the last layer, so that dimension that the encoder, the SigLIP vision encoder produces. So this is the size of each of these individual encoded patches. And obviously it needs to project these into the same embedding space of Gemma, and that's what the projector does. So it takes this dimension and projects it into this dimension. So literally input features, output features. That's very, very simple modality interface. And then of course we've got the Gemma GPT model, typical embedding layer. So this is the number of tokens. Gemma has way more tokens than a model like GPT-3, which only has 50,000 tokens. Here they went for way more tokens. But again, all of them are projected into this embedding space. And then this is the usual decoder transformer blocks that we know. So we've got 18 of these decoder blocks, the multi-layer perceptrons, layer normalization, and so on. Now, before we can pass the input to Gemma, we need, as I said, to run it through the preprocessor, which is simply going to prepare it into the right format. Now, I remind you that a multimodal LLM, especially the way Gemma works, it's going to expect some text, which is the query or the instructions that we want to execute, and the image, which is what that instruction should refer to. So let's say I'm gonna run this cell to load this picture of a peacock, and then before we can pass that to the model, we are gonna need the prompt, in this case describe the image and the image. And this returns the inputs in the correct format. Now, I want to quickly point out what this format is like for Gemma. So you can see that we get input IDs as we get with any text-based LLM, and this is just a sequence of tokens. And you can see here, these are the tokens or the tokenization of describe the image. But what are all of these other tokens here? They are all the same because they're just placeholder tokens for the image. Before this goes into the final LLM, again, what's going to happen is that those placeholder tokens are going to be substituted with the projections of each individual encoded patch into that space. So essentially, each of these is going to be substituted with the encoding or the embedding of the patches. So that's roughly how the model works. Let's do some inference on this image now. So I've got the image description as the simplest inference that we can do. And as we can see, sorry, let me just remove this print from there. It's not very nice. So as we can see, it describes pretty well that this image, we can see a peacock, flowers, plants, water, house, and trees. That's pretty accurate. Now, we can also do visual Q&A. For example, we can ask what color is the peacock, blue, what is it standing on? It's a rock, is it? Yes, kind of a rock. And here I'm also going to ask what color are the flowers? They're pink. Indeed, they're pink. So you get an idea. This is the visual Q&A task. We can also do OCR. So I've loaded here a image of a receipt which I got from Reddit. So that's a pretty bad receipt, actually, like all full of shadows and not very good. But if you ask it what is it or what it is, it knows it's a receipt. But then we can go in and say, what did the customer buy, and it knows that these are groceries. We can see what the total of that receipt should be, $100, which is correct. We could also ask things like how many bananas did the customer buy. Frankly, I think this number is an hallucination. I do not even know what banana shallots are, but I don't see the number 2 anywhere, so that's probably an hallucination. Let's try another OCR task. This is the picture of a book, and it knows that it is a book, but it also knows who the author is. So what's happening here is 2 things. It is doing OCR, but it's semantic OCR. It knows what things are. So it picked up that the author is Gianrico Carofiglio, so it knows that this is the section with the author. And then we've got obviously the title, so it also can figure out what the title is. And by the way, if you're looking for a good novel to read, 3 o'clock in the morning by Carofiglio is one very, very good novel. I do recommend that. And finally, what I want to show you is the object detection. This is something very useful that multimodal LLMs can help with. And in this particular case, if you use the instruction detect, then you can get the model to find inside the picture the specific location of a particular element. And it returns these 4 coordinates, which are essentially a bounding box. They need to be converted with this formula here into the actual locations. But once we do that, we can actually draw that bounding box. And as you can see, that's pretty accurate. Let's try to see if we can find the house in the background. So it did provide some locations for the house. Let's see if it's correct. That is pretty accurate. Let's try just another one for fun. Let's see where the flowers are. And I'm expecting that it should draw a very nice box at the bottom of this. And there it is. That's very, very accurate. That's the end of the episode. We started by looking at the general architecture of multimodal LLMs and how they rely on modality encoders to process image, audio, and video. We saw how these multimodal LLMs are trained and fine-tuned for different tasks. And then we looked at specific examples of modality encoders for images using vision transformers and contrastive learning methods. As usual, you'll find this canvas with all the additional links in the description below. If you are interested in learning more about the inner workings of LLMs, check out the LLMchronicles.com website, which has all of the episodes so far, and you can also peek at the plans for future episodes. And don't forget to like, comment, and subscribe to support the channel.